The opinions expressed on this radio station, its programs, and its website by the hosts, guests, and call-in listeners or chatters are solely the opinions of the original source who expressed them. They do not necessarily represent the opinions of Revolution Radio and FreedomSlips.com, its staff, or affiliates. You're listening to Revolution Radio, FreedomSlips.com, 100% listener-supported radio, and now we return you to your host.
Ladies and gentlemen, we are back with another episode of Cosmic Catastrophe on Revolution.radio, where information never sleeps. I'm your host, Diamond, from the Oppenheimer Ranch Project, and joining us today, my lovely partner and co-host, Leah Shaper. You are muted.
Oh, dear. Hello.
Oh, there we go. Much better. Are you getting an echo over there?
No. Are you?
Okay. Nope.
Okay.
We got a fantastic topic today, one of grave importance to humanity, one of the least known catastrophes in the common era, because, we didn't really know about it until about 30 years ago. Some of the information started coming in. The first information came from ice cores, where they noticed in the Greenland core a major sulfur spike around 1258, and they thought at that time it could be an eruption in the northern hemisphere. A few years go by, and then they find the same spike in an Antarctic core of the same time, 1258. And at that point is the beginning of one of the most brilliant, I think, displays of scientific endeavor and rigor. This is the story that we're about to tell you is about what happens when you use a multidisciplinary approach to figure out an answer. Isn't that basically what it is?
Yeah, I'd say that's true.
So what we're talking about is the 1257 eruption of Mount Samalas. No one even knew that mountain existed until 11 years ago when they found the name of it in some banana leaves in Indonesia, because the mountain isn't there anymore. It blew into the sky. It darkened the skies worldwide for over a year. It changed the weather patterns on Earth, and it killed 1/3 of the population in a single year, I believe.
Yeah. Well, and the other confounding factor is that there's another volcano right next to it. Right. So that just sort of confused things, I think.
Rinjani. So we're talking about Mount Samalas. It's a VEI7 eruption. It happened just around 800 years ago, and something like this will happen again. And if it hasn't happened in 800 years, time is ticking, because a VEI7 eruption occurs on a much shorter time scale. So we're overdue for a VEI7.
Well, and most notably, this particular eruption produced one of the highest sulfate spikes, the highest sulfate spike in over 2,000 years.
So this is a big VEI7. What we're looking at is the hole that was produced when the crust of the Earth fell into the empty magma chamber of this explosion. The eruption took place over a very short period of time. 36 hours is a good estimate. And it released 40 cubic kilometers of material up into the stratosphere. The eruptive column is the highest that has ever been determined due to particle size in the common era, a 43-kilometer high. Think about that. Ash column, straight up into the stratosphere. So in this short period of time, because it's such a short period of time, you get the maximum amount of particles shot up into the stratosphere.
So a second ago, you said particle size. Is that what you intended to say?
Yeah, they determine the column height of the explosion based on the particle size of the eruption as you go away from it. So 50 miles away, they found 6-inch blocks. You know what I'm saying?
Yeah.
And that determines how high it goes.
I thought you were referring to the particle size of the stratospheric injection, which has some bearing on the effect ultimately, but that's another conversation.
Yeah, because the smaller the particles you put up in the stratosphere, the worse the result is, because they can immediately couple with. So what happens? You get the sulfides go up there. They mix with water and they form sulfuric acid, and that's the bad particle.
Mm-hmm.
I don't really know about the chemistry. We may get into that in a minute, but take a look at the picture you're looking at. Unfortunately, on the radio, you can't see this, but you can see it tonight.
On Magnetic Reversal News on YouTube at 8 p.m. Mountain Time.
Now take a look at the caldera. When I hit 3D, look at the size of this hole.
Yeah.
This is massive. And
well,
there's
and then you can also see the reason for the potential confusion with Rinjani, which is literally right next to the hole.
That's this little, here's the top of the cone of Rinjani.
Right.
But Rinjani was here, and there was another volcano to the left of it, a little higher right here. This was where Samalas once was. It collapsed into the giant magma chamber hole after it released all this material, 40 cubic kilometers, and it's still hot. There's a little active volcano on the bottom here that's still active. So it's been continuously moderately erupting since 1257, but nothing significant. It would take tens of thousands of years to build up another big mountain here to blow it up into space again.
Yeah.
So I don't think we have to worry about another big one coming from here, but there are thousands of active volcanoes on Earth, many of which we don't monitor, which means this could happen at any time.
Yeah.
No way of knowing. We do monitor some bigger calderic type volcanoes, like in the Caribbean, in Italy, places where there's huge populations and they are monitoring it. But like parts of Indonesia are almost uninhabited. So there's not a lot of monitors going on these volcanoes.
Right. What a weird place to live, right? Like obviously you've got really fertile soil, but then you have so many volcanoes in this area, like you're just rolling the dice all the time.
Well, it is kind of weird to think about that. A lot of people don't have the wherewithal to move from the place that they're born. Like most people in Philadelphia, I would say there's like 25% of the population. They never leave. They only stay there. And then they have more kids that stay there.
Right.
It's very bizarre.
Well, we've talked about this before too, that even in Pagosa, right? Like we know some folks that live in town in Pagosa, and not only do they not leave the area, but they don't even leave the town of Pagosa. And there's such beauty all around, and yet they don't explore it at all. I guess it just goes to show that we're creatures of habit, right? We're used to what we're used to, regardless of whether or not it's positive or negative.
Yes, indeed. So back to the fascinating scientific story here of the Mount Samalas eruption and how they came to the conclusions. So they determined that there was these sulfur spikes from the ice cores about 30 years ago, and then they found them in Antarctica. So we're getting closer and closer in the timeline. The next thing that goes down is some dendrochronologists find some trees that line up with this time frame in the sulfur spike, and they look at those and they find that it was a very cold summer and winter or entire year in 1258 or so, around that time, 1259 as well. And then they found more tree rings from other areas. So not just in one place. They start matching this up globally through trees in the Northern Hemisphere.
Mm-hmm.
And so now you're onto something. We've got this major climate shift and a sulfate spike. Clearly, it's a volcano. And now they have to determine where the volcano
Which it is. Right.
So,
right. And the first place to look ends up being equatorial, specifically because you see the same sulfate spike in the Greenland ice core as you do in the Antarctic ice core. The only way that happens is if you have an equatorial volcano.
Yeah, and we have done in the last decade or so some great geochemistry with erupting volcanoes. And so they went and looked and found the highest sulfate-rich volcano to be the first candidate, and that was El Chichon. But when they went to study El Chichon, they clearly eliminated it because it didn't have any evidence of an eruption that could create 40 cubic kilometers of material.
Mm-hmm.
Clearly,
and wasn't the timing off as well based on the analysis of the pumice? Like the pumice was too agglomerated. Like the pumice there was much older than this volcano eruption would indicate. Or maybe that was a different volcano they looked at.
what Leah just said is the pumice is almost fused and lithified into a rock. That usually shows of an older age, probably in the thousands to tens of thousands of years.
Mm-hmm.
So what they're looking for is fresh ash, basically.
Mm-hmm.
And also clearly a caldera, because in order to erupt 40 cubic kilometers, you're going to need to probably leave a big hole in the earth.
Mm-hmm.
So they were looking for a caldera, and quickly they found one on the island of Lombok. They found this caldera that was dated. This was initially dated to a 10,000-year-old eruption, but still a Holocene eruption. But you can clearly see the scarp here is very crisp.
Mm-hmm.
It wouldn't be this crisp all the way around, all of these features, if it was 10,000 years old. Additionally, there's an active volcano in the bottom, which means it's still hot.
Mm-hmm.
So just based on that assumption, they took a chance and they went out here. And lo and behold, they determined this is a very young explosion. And they began then looking for evidence of the type and size of eruption it was. And they found that evidence in the form of pumice rock.
Mm-hmm.
There are huge deposits of pumice, 100 feet or so, kilometers away from this volcano in every direction. And they're all close to the surface, all the way to the surface, indicating this is a recent event. Now, do you have anything to add as of now?
Nope.
Okay. So based on everything they know that now, and when you travel to the edge of the island of Lombok, you find 100 feet of ash. It means that everybody and everything on this island was killed.
Yeah.
On top of that, you can even see, look at some of these, you see these pyroclastic flow marks?
Yeah.
This is where the flows are going to come. This is just from Rinjani. Has nothing to do with this one. But when this baby exploded, the pyroclastic flows moved out here and here and here in 3 directions, which you can almost see based on the topography, how that would happen.
Mm-hmm.
You can also see what happened here over on this island. You see that there's no green here.
Mm-hmm.
This especially patch here was scoured and devastated by a tsunami that came across, maybe multiple. I think they found evidence of 3 tsunami waves.
Yes.
On this island.
Yeah. Yeah. So like a giant tsunami that essentially happened in 3 stages. Probably coordinated with the volcanic stage, right? Because there's like 3 or 4 volcanic stages. The final one being the collapse of the caldera. So the previous 3 would have contributed to the tsunami.
It was probably 3 over the 36 hours. 3 major pyroclastic flows came down here. Boom, boom, boom.
Mm-hmm.
I was thinking there would be some sloshing because it's such a small channel here.
Mm-hmm.
But did you see the tsunami deposits themselves? They're only a foot thick or so for each wave. So it's not that big of a tsunami.
Yeah.
I would say 10 feet, 20 feet, something like that. High enough to wash inland for miles.
Mm-hmm.
So this is now, we're looking at the largest eruption in the Common Era, and it did terrible things. Before we get to what happened when this baby blew up, let's finish the scientific story. So they found all this evidence. Now, how do we know this is the eruption at 1257? Well, they went into the historical documents. So they had already dove into the historical documents worldwide and found evidence in China that in 1258, 1259, terrible things happened and people died. They found the same evidence throughout Europe. In 1258, 1259, bad things happened and everybody died. They even found a word that had never been used before, wasn't even in the language of the text of the script, ancient script they were looking at, but it was determined to mean dark year or dark fog.
I can't remember now what I was going to write that down, what that word was and what it meant.
Yeah.
Oh, I forgot. And you know, bear in mind too that the texts that we're talking about from Indonesia, they're not contemporaneous texts. They're not texts from the 13th century. They're only about 300 years old. But they're the passed down recollected accounts of people who live in the area.
Yeah, it says 3 written sources from Lombok, Indonesia, provide descriptions of the ancient landscape of Lombok and the population's response to the Samalas volcano eruption in 1257 CE. So when these guys went down there, they found some of these, they found a historian there in far away. I don't know where they have these texts. Do you remember where they're stored? Are they on Java?
They're on Lombok.
Oh, they're now on Lombok.
I believe I don't know if that's where they're stored, but that's where they're from. Or
Okay.
one of them is anyway. There's three books, and one of them is the essentially I get what you would call it's the Babad Lombok, and it's from Lombok.
Yeah, and what it said is specifically in 1257, Mount Samalas exploded and everybody died, essentially.
Mm-hmm.
And their minds exploded because they never heard of that volcano before. And they now had all the pieces of the puzzle together. They had solved the mystery of the sulfate spike in 1258.
Mm-hmm.
And so the amount of scientific endeavor that has come out of that discovery till now, they did some modeling to determine specifically prior to the discovery of this when the eruption took place. They already thought the eruption would have taken place in 1257 based on computer modeling. And now they have this historical account which corroborates it exactly.
Yeah. Well, and the other clincher is that when you examine the geochemical evidence of this eruption and you compare it to what is in the ice core, you get the exact same chemical signature. So that's the nail in the coffin right there. I mean, you can't deny that this is the same eruption corresponding to that spike in the ice core record.
Yeah, they also took, they did the geochemistry of the melt inclusions. Is that what you're talking about?
Yeah.
Yeah, so they found a piece of ash up in the Arctic, and they matched it with the piece of ash they took right here on the flank of the volcano.
Right.
And they
it's
were
exactly
identical.
The same geochemical signature.
Yeah, so it is like, this is a scientific case that this is not a theory anymore. This is scientific fact that what we're looking at is what we know.
Mm-hmm.
That is not often the case. In fact, in one documentary that you and I watched, at the very end, there was a scientist that said, we got lucky. We got very lucky. Because what are the odds?
Well, and what I find kind of extraordinary is they went through the search for it was obvious that it was an equatorial volcano. So, they go through some of the known equatorial volcanoes, and, even just by kind of looking at it from like a map perspective, we need a caldera that's, roughly of a certain size to match the amount of material that would be injected into the atmosphere and the stratosphere. It needs to have pumice fields nearby. And like after a few candidates, they found it. That was lucky. Because how many equatorial volcanoes are there? There's probably hundreds, right?
There are over 100 just in this small area of the chain of islands in Indonesia.
Right. Yeah, so thankfully there was enough criterion with which to kind of narrow that down and sort of quickly go through candidates, but they only really had to go through a few to find Samalas, a volcano that we didn't even know existed.
Right, and now we do. And now we know it killed everyone on Lombok. Every man, woman, and child, animal, plant, everything was covered in the least amount, 100 feet of pumice. And so this was a 3-phase eruption. The first phase was the raining down of pumice for 6 hours, then a major pyroclastic flow, then another pumice rain, then another pyroclastic flow, and then the final explosive episode, which is not really explosive. It's more desplosive. It's when the crust falls into the hole, and that is a catastrophic event in itself, pushing out the rest of the magma and gases. So that's the final big boom.
Yeah. Now, what would be super interesting is if somebody attempts to find what was the kingdom of Pomaton in this area that now no longer exists because of this eruption, right? It would be like a Pompeii. It would be like finding a Pompeii on steroids, right? This is way larger than Pompeii.
How big it was the city?
I don't know.
Okay.
Yeah, but it was a kingdom, and the books, the Babad, what is it, Babad, Lombok, and the other two books, Babad, whatever, I don't remember their names.
Babad. It just says Babad.
Well, one of them is Babad Lombok, and then there's, hang on one second, two more books. Babad Suwung, Suwung, and Babad Sembalan. I'm assuming that these correspond to nearby islands. So those books, what they talk about are the like recovery efforts, like what people did to get away from this eruption and what happened after the fact. And the supposition is that the recovery really took like 100 years, but by that point, the new kingdom is a completely new kingdom at that point.
Yeah, this is one of the second half of the show. I wanted to get into this, and this is one of the effects of what happens when these volcanoes go off, is that it is empire ending, and not just for the local people. This happened globally, where supply chains were affected all the way back in 1200. Now listen to this. The big mystery of why the Pueblo and the Anasazi disappeared by 1300 has been answered. North America was dark for years. And if you were out in the desert Southwest and it dropped 2 degrees C overnight, you would move south. The evidence is by 1300, all of those clans had moved into Mexico, south. So clearly we have the answer why the Anasazi and the Pueblo and all those people, the cliff dwellers, left by 12. They left in 1258. I can tell you that. That was the year they left. The year of the dark fog.
Right. That's very interesting. And then, of course, there's, and we'll get into this, I think, in the second half of the show, but there's potential for a lot of other cascading effects elsewhere in the world, and probably the best documented would be Europe. And some of those things, it's not exactly clear if they're connected to this or not, just based on the time frame, but we'll get there.
Yeah, so do you have any other interesting tidbits on the historical accounts you wanted to hit?
Nope.
All right. Let's talk about the climate response to the eruption. It says here, revealed by Proxy records. If scientific papers scare you and big words or words you don't understand scare you, all you need to do is look up the definition and keep it moving. Because proxy isn't a scary word. It just means another data set that's not temperature. Something else that may mimic the effects of temperature. So they use that instead.
Well, and even if you are familiar with reading scientific papers, you may still need to do the same thing. I often find myself looking up specific terminology that is specific to that field that I don't have background in, and then I can just look it up and move on.
So did you read this paper? Because I only have the abstract.
I only have the abstract. I wasn't able to access this. I wish I had.
Well, let's just first go over the science of what they found to get you up to speed. This is the sulfate spike. So the red one up here is Greenland, and the blue graph down here is Antarctic ice cores. And we did
we reviewed this around 536.
Yeah, we showed this because when we did, I think you said 2 shows on the worst year to be alive.
Yeah, it was February of 2023. We did 2 shows on 536 AD, and we basically concluded that there was probably some kind of cometary impact or like debris from a comet that maybe stimulated several volcanoes. Because
one in Iceland, which is this spike, because there's no 536 spike in the southern hemisphere, just the northern hemisphere.
Right.
So this would be Laki, the eruption of Laki. And then I think Ilopango in 540. Didn't we have that?
Ilopango was 5th century.
Okay.
Yeah. There was some debate about that for a long time, about when Ilopango erupted, and I think the final conclusion, and people still talk about Ilopango in relation to this event, but as I recall, that's mistaken based on some papers we read, because it seems that the Ilopango eruption was like a century earlier.
And again, 536, worst year to be alive. 1258, a higher sulfate spike. This is a bigger event. Yeah. So it's clearly 1258 and 9 were the worst years to be alive.
Yeah. By the way, 432, 434 here, that's probably Ilopango, I would guess.
Oh, right. That's it. Yep.
And which makes sense because the spike is bigger in the southern hemisphere.
Exactly.
Yeah. But by comparison, so this is interesting to think about, right? Because we say 536 was the worst year to be alive. In reality, and this is not reflected really well on the northern hemisphere graph here, but the sulfate spike for 536 is overall way smaller than what you see for 1258, generally speaking.
And 626 in the northern hemisphere. What happened here?
Yeah, that's a good question. It's funny. I was looking at this graph. It was a different version of this graph this graph looks distorted to me for whatever reason. Like the proportions are not the same, but we'll have to look at a couple of data sets and get a better sense of that. In any case, so what I was going to say is that, historically, it sort of sounds like 536 was worse, but I think maybe 536 was worse because there were other confounding factors, like potentially a cometary debris impact, whereas the effect of Samalas was enormous compared to the eruptions around 536.
Yeah, and then the rapid onset of the Black Plague in 537 didn't help out. So it was the direct correlation of Black Death with the volcanic eruption and starvation, adding insult to injury that caused so much death.
Yeah.
The Black Plague doesn't come around until about a decade after the Samalas eruption for the second time. Isn't that interesting?
Yeah, so I was looking into this a little bit today, and
or is it 100 years? Is it 1350?
The onset of the Black Death in Europe is 1347. And the story is that that there was a ship that arrived in Sicily from China. So it went from China to Constantinople and then to Sicily. And when it arrived, most of the sailors were dead. And a few of them were still alive, but they were really, really sick. They were ordered out of the harbor, but it was already too late. So there's kind of two things going on. Well, let me backtrack even further, right? So that's 1347. And that lasted until about 1351, 52, where like 30% of the European population died as a result of the bubonic plague. But this is confounded by a lot of other stuff. This is interesting, 1314 and 1315 were the wettest years ever seen between 1300 and 2012. Super, super wet. And the result of that was that there was a huge famine prior to the Black Death that started around 1316. Because of all of this excess moisture, there was terrible crop failure. There was also a tremendous amount of disease amongst cattle and sheep. Like 80% of those livestock died. So there's a lot going on here. And I think we'll get to this, but if we look at the proxy temperature data for out of the ice cores correlated with world events, this one. So you see where it says the Great Famine and the Black Death. So that's like 1347.
Yeah.
So somewhere in this,
here's the Samalas eruption. This bottom.
Well, but I think it's before that, right?
Yeah, it's right up here. This is 1257, and then you get the drop down in a few years.
Right. So you already have a big temperature drop that's happening. Then Samalas happens. There's even a further temperature drop. We get, it's decades later, so I don't know if it's related. It doesn't exactly make sense, but you get this incredibly bad weather in Europe of all of this moisture. So the Black Death is being preceded by temperatures that are already falling, that are unseasonably wet by a long shot. And a famine. So you already have a population of people whose immune systems are tremendously taxed. Right. And then you throw in the fact that this is an important principle of bubonic plague, right? It's carried by fleas, and the organism that causes bubonic plague is always around. The difference is that when the temperature drops to a certain point, what happens is that it causes like a blockage in the digestive system of the flea, and their own contaminated blood kind of gets regurgitated back into their bodies. Now, normally that doesn't happen. Normally the flea kind of processes the organism and then that's the end of it. But when this temperature drop happens and it's affecting the fleas, then the microorganism can survive the flea, and then it infects rodents, and then it spreads to people or whatever. So, and it's also contagious. It's in the air, and it's transmitted by touch. So it's like highly, highly, highly contagious. So like this organism is always around, but then you've got a population of people who are already terribly taxed by famines and cold temperatures and bad weather, and then it shows up on a ship because it's happening elsewhere in the world, and everything goes to hell at that point. So it's like, I don't know exactly if there's a connection between Samalas and everything that happened with the Black Death and prior to that, but it does seem like there's like a decades-long cascading effect that helps sort of bring all of this on. And it is interesting that the eruption of Samalas precedes the Little Ice Age as well.
Yeah, so we were dropping down here in temperature. We were trying to recover, and then Samalas darkens the world, and then it's terrible. And then it stays terrible.
Yeah, for a long time. Oh, this is interesting. Listen to this. There's outbreaks of bubonic plague for generations after the Black Death. The list of years where it cropped up again in specific places: 1382, 1466, 1559, 1647, 1666, 1679, 1710, 1720, 1770. And this is all during the Little Ice Age, right? Because the only way this is possible is if it's cold enough.
Now take a look at the spikes here in the last 4,000 years. We've got the Minoan warm, the Roman, the medieval warm, and the modern warm. Every time we get a spike in temperature, we come straight down, folks.
Yep.
Every spike, we are at a spike again. A lot of times we have a double peak like this. This is a double peak. Here's a double peak. Here's a double peak.
Mm-hmm.
It is about to go straight down. And as it goes down, we get volcano erupting here. We've got a volcano erupting in 536. As it goes down, bad things happen, and it gets worse and worse.
Mm-hmm.
So humanity is not prepared for what is obviously displayed on this graph. They've been duped into thinking that this red line here is because of CO2, and it's going to continue to go up forever.
Mm-hmm.
That's crazy. So when it goes down, what will the population think?
Right. I mean, it's always really funny to think too about, the narrative about CO2 increasing temperature when you look back at like the Minoan and the Roman warm periods, which were even warmer than today. But it's funny as well because we've seen in the last few years some revisionist history about that. Media claiming that the Minoan and the Roman warms weren't nearly as warm as we thought.
Yeah, we're so dumb.
And it's like, well, actually.
Yeah, so you were saying it took 3 generations before anything returned to normalcy in this region. And what came back was 3 generations later, completely different.
Yeah.
And by that time, they probably have like stories of the big eruption. It's more myth. It's forgotten.
Yeah.
And people go right back on the side of that volcano and build again.
I mean, I actually find it pretty extraordinary that though these texts that mention this eruption are only about 300 years old, that the story of the eruption carried on for that long. That's pretty amazing.
And the specificity.
Like that it wasn't completely forgotten.
Yeah, the specificity, the name of the volcano, the exact date.
Yeah.
It's because Indonesia was populated, all the islands were. So there were people that survived and they could tell the tale. So that was probably written in every book on all the remaining islands forever. And
yeah, but it's centuries of like oral tradition being passed on, which I find extraordinary, which tells us something that we really have to listen to the oral traditions of cultures, right? Like for example, Native Americans, right, who have a much stronger oral history than anything else. And yet archaeologists tend to not even talk to, let's say, like just as an example, the Navajo people will tell you that the official archaeological narrative of who the Anasazi were is incorrect. But yet the Navajo really haven't been interviewed by these archaeologists. But those oral traditions can be really strong. So we should listen to them.
Yeah, because they're probably correct.
Right.
All right, now the big question. How massive volcanic eruptions can alter global temperature? It's not a theory. We actually have here. They do a couple of things. So here is El Chichon, 78, 79. Looks like 1982 El Chichon.
It was 1982, yeah.
What volcanoes first do, if they're big eruptors, is they reduce the solar radiation on the surface because they block the sun. And you can see here how significant a VEI7 can block the sun.
Well, and the sulfate emissions, right, producing sulfuric acid in the atmosphere, stratosphere or atmosphere?
Stratosphere.
And that creates a reflective effect on its own.
Yeah, so that's what's going on here immediately.
Yeah.
Now, these two aren't stratospheric, so this is atmospheric dimming, but on a large scale, which still makes it cold down on the ground.
You know, it's interesting. I was looking into El Chichon a little bit, simply because it's in our lifetime. And I was reading that the climactic effect was probably moderated by the ENSO cycle at the time. So it wasn't really very obvious.
Yeah, and it's only a VEI7.
Well, that too. Yeah.
So here is a longer span. This comes from Berkeley Earth, and it's showing all the eruptions all the way back to 1750. You can see some significant changes in Earth land temperature here, up to almost 2 degrees C here with Tambora and Laki. And you can see Krakatoa as a minor blip. We've got other blips here, small eruptions. They really don't do much. Agung, little blip, little Pinatubo blip in 91, I think. And here it says, look at this. Post 1956 rise attributed to IPCC to humans.
I don't understand this red text in the middle. That says carbon dioxide in volcanoes. Like, what are they even pointing to? And what are they talking about? It's like the line also refers to carbon dioxide. Is that the suggestion?
This is the general temperature rise on Earth since 1750. It's 1.5 C. So this is
right. But why are they pointing to the line and saying carbon dioxide in volcanoes? Like, what are they talking about?
Carbon dioxide in volcanoes causes the temperature on Earth. That's what they're claiming. It's like IPCC climate science. So as carbon dioxide is driving the temperature up, these volcanoes are fighting it by shooting it down. Boom. Yeah. This is not actual science. This is the scientism they use.
Yeah.
So, wow, look at that boom right there. That's the Pinatubo 91. And so all of these just minor blips in the temperature graph on Earth. Here you can see since the 40s, we've had some volcanoes make it a little colder, but nothing spectacular. It's the super volcanic eruptions that are going to kill us. Not these, fear mongers that are claiming a VEI5 or 6 will change the Earth. It didn't. Mount St. Helens went off and it killed 11 people. That's about it. But the problem is when we have a VEI6, a very high 6, low 7, then things will change, especially if it's equatorial. Now we have to worry about, there is a chance for a large eruption like that coming from Iceland that could last for years. So you can have a lower level eruption that continues for years, and then that will affect the climate by darkening the sky continuously. And any effect like this, we will be unprepared for. So the supply chain will break down on its own as there's no more supplies to put into the chain. People who rely on imported food, like Hawaiians, will die immediately because there will be no food coming there. If the sky is dark and you can't go to your job anymore, you're trying to keep your family alive, you're not going to pilot the ship to Hawaii to save those people. And some people get very angry at us when we tell them this. They say,
Yeah.
how dare you? Of course, people are going to save people. I'm like, they're going to save their family first. Trust me.
Yeah. Well, also at a certain point, there's only so much you can do, right? Like we've talked about this in respect to, let's say, the potential for a major solar flare or EMP that takes the grid out, and like all of the cascading events that happen with this that would make recovery extremely difficult. And this is no different, right? Like there's again a cascading effect here where you lose some amount of sunlight, temperatures drop, that causes crop failure, which causes famine, which causes not necessarily starvation, but propensity for illness. Like that's the real kicker here, right? Like, and that's one of the things that happened with this eruption. It was the famine that was a result of crop failure that led to sickness, generally speaking. It's the same thing with, the famine preceding the Black Death.
Yeah, and what also is happening here, if you have malnutrition and anything happens to you, you nick your toe, you're dead.
Right, that's kind of what I'm saying.
Yeah.
Well,
So
I was just reading something else too. We have this other paper.
Yeah. Do you have the historical accounts? Is that what you're going to go over from Europe? Oh,
no.
Which paper?
The Reconciling the Climate and Ozone Response.
Yes.
This is from 2020. I find this paper somewhat useful, but in a limited way. One of the things that they talk about in here. So, okay, right off the bat, they tell you that based on the geochemistry on the ground in analyzing this volcano, you've got 158 megatons of sulfur dioxide that were probably released with also 227 megatons of chlorine and 1.3 megatons of bromine. And what the reason they're talking about that is because the injection of halogens like chlorine and bromine into the atmosphere would have major effects on the ozone. And when ozone gets disrupted and you get a lot more UV radiation coming in, the extra UV radiation in and of itself can contribute to illness. Your immune system not functioning the same way, which is pretty interesting.
Yeah, and when we get up to a VEI7 eruption like this, it's not like the VEI5s and 6 we saw on those graphs that affect temperature in a very small way. Mm-hmm. These affect long-term temperature for years. Yeah. And not only that, because of the sulfur dioxide that's up in the stratosphere, it's not only reflecting sunlight back out into space, it is actually capturing some of the heat from the sunlight, and it begins heating the stratosphere while it's cold on the surface. Right. And if you know anything between when hot and cold mix on the surface, you get a storm front. This type of storm front is in our air column on the planet. And what it does, by heating the stratosphere unnaturally, you wreak havoc down below in the atmosphere. The normal weather patterns that we're used to, east to west with the jet stream and the zonal flow, none of that exists. Yeah. There is literal chaos on Earth. It rains in places it never rains. It snows in places it never snows. It is complete chaos. Everyone is taken off guard, and that's what leads globally to malnutrition, because every region is affected in one way or the other. Some areas get continuous rain, which you can't grow anything in, and other areas dry out and you can't grow anything in. I mean, it is literally, it's hell on earth. Yeah.
Well, and the ozone depletion has a similar effect temperature-wise as well. So you add that in on top. And, this paper's funny because, once again, this is a paper that's based on modeling, right? So they plug their data into a bunch of different models. And one of the things that they concluded as a result, and I always question the models because, how much of these models are based on an idea in atmospheric chemistry that isn't really true about CO2. But one of the things that they conclude is that the halogen injection could only have been minimal And I think that they may be wrong in this effect. Like just the proportion of the geochemistry on the ground, 158 megatons of sulfur dioxide versus 227 megatons of chlorine. Like, and then if you look at the longer term effect, will potentially affect temperature wise of the little ice age, like this is what leads me to think that it's possible that this eruption actually had a century long, if not longer, effect on the climate. I mean, I don't know that, but the way that these models worked out didn't really make sense to me. You know, they're kind of suggesting that it all would have been over, the effects would have all been over with within 6 to 10 years. And according to this proxy data, that doesn't necessarily seem to be the case, unless there's, you know, I mean, there is something else going on with the little ice age, right? We have less solar activity during this period, right? So that's obviously a contributing factor. But I kind of feel like this paper really underestimates the effect of this volcano overall.
Right, like the world underestimated the effects of Hunga Tonga.
Yeah.
When you put 10 to 13% more moisture in the stratosphere, you're going to get heating at the surface. You're going to get a global warming effect because it's essentially trapping heat, keeping it on Earth. So there will be a spike in temperature. And you're also going to get a huge spike in flooding rains worldwide once it's distributed across the globe. And we've seen that.
Yeah.
You can even look at a graph of the stratospheric moisture, and it's still up there years later. They said it'll be all gone in 3 years. Here we are, and it's still all up there. They don't know what they don't know.
Yeah, well, and so for that reason, I really think that we should also look into the conditions that I mentioned earlier, 1313 and 1314, which were the wettest years in a 700 plus year period that led to crop failures and famine. Like, what was going on? Was there something else happening that caused all of that extra moisture? Is it actually related to the Samalas eruption? Like, I think we should look into that time period.
Well,
Because that might tell us something about the potential longer term effects of a volcano like this.
Yeah, it could be just increased cosmic rays during the mini ice age caused lots of rain to occur.
Yeah. But still, that is really, you could argue, even prior to the little ice age.
What is?
The 1313 period, right? Because, you know, according to this, but that's 1347.
Yeah.
So anyway, yeah.
Yeah, so that's also explains, I mean, we've explained this before, the phenomenon of mud flood. Like, people think that what we're seeing is unprecedented flooding. No, you haven't. If we were alive 600 years ago, 700 years ago during that flooding event, it would be 100 times greater than anything you've seen now.
I find it bizarre that people think that their own little lifespans, like the maybe like 40 to 80 years that they've been on the planet and what they've seen in their own lifetime, is somehow indicative of like what can potentially happen on Earth via natural causes, so that it has to be some man-created conspiracy. It's like, you've only been here for like the smallest blip of time. Like, what is it that you think you know about how things are supposed to be? It's bizarre to me.
Yeah, the government wasn't steering weather patterns 4,000 years ago. Neither is it doing it today.
Right. Like that, and that's the real thing that tells the lie, right? That these things that people think are unprecedented or have happened before. So on that basis alone, you cannot conclude that the variable that caused the thing is the modern government. You just can't.
Well, and the fact that the governments are inept at best, like, come on.
Right. Now, a better theory, like, I mean, this is still terrible, but like, based on the ineptness of government, a better theory would be to say something like Elon Musk caused it, right? Because Musk is capable of things that no government has been capable of in hundreds of years. So that would be a better theory, but it's still really bad.
Yeah, but government shills like Neil Tyson deGrasse will cover it up. He recently said that Elon Musk has not done anything for the aerospace industry. It's all NASA. NASA owns everything Elon Musk has done.
Right. Like Elon just caught a 20-story rocket with these arms, and that somehow NASA's responsible for that.
Right. NASA's responsible for giving Boeing a contract that wasted $7 billion, was 7 years late. And when they finally launched it, it was a failed spaceship, and it stranded 2 astronauts on the space station who are still stuck up there till next year when Elon Musk is going to fly up and save them.
Right. I'm telling you, I've said this 1,000 times now. Elon Musk is freaking Batman. He is. Like, he exactly fits that archetype perfectly. But of course, the establishment refuses to recognize what he has contributed to society and what he's capable of.
Now, unfortunately, all of that might be for naught if the sun acts up and shoots a solar flare in the next decade that fries the grid and destroys humanity. None of that matters. It will take decades or centuries to rebuild, just like it took the people of Indonesia to rebuild after the Samalas. It takes more than 100 years.
Yeah.
So when the next VEI7 goes off, and it's overdue, it'll probably happen as we're dropping down during the next grand minima, which could be starting next cycle. The cold part could be next cycle 26. Then we should expect a VEI7 eruption to occur.
Yeah.
The most logical time when we've done research on this is during the solar minimum. So it would be the bottom of the cycle, because that's when you get increased cosmic rays that can heat these types of volcanoes to go boom.
Yeah.
And so what will happen is you wake up one morning, it will be very bizarre outside. It will look weird, and it will stay weird for years.
Yep.
And we're going to experience no sun, it's diffuse sunlight. You will never see the sun for over a year until the smoke and the haze clears. And that takes quite some time, because we're talking about what's trapped in the stratosphere blocking the sun. That takes years to come out.
Well, and even if the stratospheric effect is minimal, like even if the sunlight is only dimmed a little bit, that still is going to have major ramifications for all life on Earth, right? Because again, it impacts your production of vitamin D, and generally speaking, is going to affect the functioning of your immune system. And then, throw on top of that the potential for famine and malnutrition, et cetera, and then the cascade begins.
Yeah, so the number one prep you can have in the event of this type of situation, I think, is nutrition in the form of green energy powders, maybe a few years supply, something that you can take a little less of than it says to take, but it will give you the micronutrients you need. You need micronutrients.
And vitamin D.
Yeah.
vitamin D supplements, seriously.
But you need the right type of vitamin D.
Yeah. D3.
Not those gel caps, those cheap gel caps. That's not the vitamin D you want. The one that's just D3 and it costs $4.
What's wrong with those?
Someone said that you flush that through your system, it doesn't uptake very well. Is that what we're taking?
We are.
Yeah, well, I take vitamin D every day because I'm out in the bright sun here 200 days a year.
Yeah.
So you really need to get out and get sun, especially if it's hazy out after a VEI7 eruption. You should be working with your shirt off.
Yeah. Well, and again, like you said, micronutrients are also extremely important, right? Like any mineral supplements, because, you can take all the D you want, but if you don't have the right amount of, let's say, K, magnesium, selenium, all of that stuff, like it's not that useful to you without those
and you can research wild edibles. There'll be weeds that continue to grow during the darker days, like clover, and alfalfa, that you can eat small amounts every day and get these micronutrients. So research your plants, or at least buy a book on weeds in your area, or join a group on wild edibles. If you live near a city, there is a wild edibles group near you that may save your life. Because it's not a question of if, it's a question of when.
Right. And as we've discussed, over the dinner table, it's been a long time since there's been like a VEI7, that's this far reaching. So it would suggest that we're overdue, which is of concern. It's been quite some time.
Yeah, and we just discovered its existence in the last few decades.
Right.
That's even more telling.
Yeah.
Great show.
We always have a happy, joyous story to tell. Find us tonight on Magnetic Reversal News on YouTube at 8 p.m. Mountain Time.
Listen to Revolution Radio at freedomslips.com, and we'll be right back after this message.